There we go. All right. So how do we make use of a struct? Well, that's pretty easy. You can write a function. So we'll go ahead and write the same function that I did with cisp310, which is comparing two dates and find out whether the first one is before the second one. Okay, that's all we're going to do. So we'll say u in a underscore t, because in C there's no such thing as a Boolean type, so you can only have an integer that is either 0 representing false or anything that is non-zero representing true. So u in a underscore t is before, is the name of the subroutine, and then we say struct. The first one points to the first date, so we'll say this is a pointer to date 1. Oops, I need to represent the type first. So this is a pointer to a date, and then we have another one. You can pass a date or any object or any structure by value in C as well as C++, but it is very inefficient, and that's why usually it is not considered a good idea. In this case, for those of you who really like to make things so that the compiler can do as much as it can to help out, I know I'm going to move this. There we go. So if you want, you can add const before the struct, because this way you're basically telling the compiler, make sure I do not accidentally change anything in any one of the structure, because the whole idea of this function is really just to compare. It is the less than version applied to dates. Are we doing okay so far with this? Okay. So now how do we write this function? Okay. So we'll go ahead and go here. Assuming that you took cisp360 before this class, so the way we access a particular member inside the structure, and we also did this when we dealt with the floating point number program. So I think some of you still remember how to access a member from that class. So we can now say if PD1 points to year YS 1900 is less than PD1 points to YS 1900, then it is conclusive, isn't it? Because if you look at the years of two dates and one is already less than the other one, you don't really need to look at anything else. You can basically conclude at this point that yes, the first date or the date represented by the structure pointed to by the first pointer is less than the second one. So you can just return a non-zero value. You're done. So are we good so far? Oh, right. Yep. Thank you. There we go. And then what if it is not less than? If it is not less than, you have two cases, because one can be greater than the other one, or it can be equal to the other one. So in C and C++, you don't have the shorthand that can say, okay, depending on whether it's equal to or less than, we do things differently. So you kind of have to do it in this kind of long and tedious way. Okay. So if we ever get to this else statement, what does it mean?
That the if was not satisfied.
That neither condition is true, because remember, this is the first condition, but we don't get to this part until the first condition is false. And this is the second condition. We don't get to this else unless both the first and the second condition are both false. But by the time we get here, we know the years are the same. So if the years are the same, then you can look at the month, right? I mean, to determine the order. So now we can now compare the month of the first date versus the month of the second date. And if it is less than, we can return a non-zero, because that is conclusive that the first date is less than the second date or before the second date. Else, we have to compare again. So the assembly implementation of this is actually quite a bit easier, but we'll see how that goes when we get to that. So now we compare the day of month, okay? Because if I get down to here, that means the years of the two dates are the same. The months of the two dates are also the same. So now we have to look at the day of month in order to find out which one is whether the first one is before the second one. Yes.
Do you have the case where
If it is greater, then I think I did. Oh, I guess not. Okay, so we have to catch that one first. Thank you. Yeah, the assembly code of this is actually significantly easier compared to the C code. And that's because in assembly code, we can go for conditional branches in a much more flexible way than we can in C and C++. So in this case, we have return false because that is for sure. Then we can, okay, I'm just going to be a little bit lazy here and say return PD1 month is less, oops, day of month is less than PD2 month, DOM. There we go. Okay. Because you can, return the result of a comparison directly. There's nothing wrong with that approach. So are we good so far with the logic of this code?
So in that case, if it's the same or greater, it would be false.
Hmm?
If it's the same or greater, it would be false.
That is correct. Yep. So it gets the job done. All right. So given this is the subroutine that we are implementing, so now we need to look at, okay, I'm missing a curly brace somewhere. Oh, there we go. Okay. So this function is now done. Now we use a main to test it, okay, to see whether it works or not. So here's main. And in main, I will need two local variables. So I have struct date tax birthday, BD, and we'll have Dave's, Professor Fox, birthday. And the initialization, it's going to be a little bit tedious because you have to initialize every member separately. So YS, 1900, it needs to be initialized, differently. I'm going to make up a fake number here. So this is totally not my birthday. So the month is, moth. It's October 1st is DOM. And then we'll make up a birthday for Professor Fox. Well, since he's retiring, I'll give him a retirement gift and say that he is much younger than I am.
Can I ask if you use negative values?
Negative values. I would pretend I did not hear that. Okay, so the code is not really important. Okay, in the other class, we were trying to, exercise the logic in the subroutine a little bit, but in this class, that's not important because what we want to do is to illustrate in assembly how do we do all of this stuff. Okay, so now we need to call the subroutine, and I'm not going to utilize the result of the function call. I'm just going to call the function. Okay, is before. Okay, but now we have to be careful because we are passing the address of a structure, so we have to take the address of tax BD, tax birthday, and also Dave's birthday, and pass those two pointers along. And by observing register A when everything is done, I know whether it is correct or not. Okay, so I'm not going to store the result into a particular variable. I'll just call the function and toss away the return value. Are we doing okay so far with this? At least the C code. Okay, so the C code is fairly clear. So now the question is, how do we do all this in assembly code? So we'll go ahead and open another mouse pad. And the first thing we need to do is to say, what about the structure itself? How do we define a structure in assembly code? Okay, that would be the first question. So there are many ways to do it. The way that I'm going to do it is to use a whole bunch of labels. So the label is going to be in the form of date, the name of the structure, underscore, and then the name of the member. Okay, so this is basically saying, okay, where can I find YS 1900 as a member of a date structure? That's the question. But it is relative to the beginning of the entire structure. So it is kind of common or kind of makes sense that the first member of an entire structure will be at the very beginning of the entire structure. Does that make sense? Okay, and the second one is right after the first one, and then the third one is right after the second one. So that seems to make sense. So that means this particular label simply is defined to be 0, because as the first member of a structure, it is at the very beginning of the structure itself. So the offset of the member from the beginning of the entire structure is 0. Yep.
So I'm keeping front of mind, when would you decrement the, would you do like decrement D and then make a label and then decrement D and then make the next label? Or would
Nope.
you,
No, this is label definitions are independent to instructions. Because instructions is what the processor actually would use to execute stuff, but label definitions is not going to be in runtime. So the effect of labels is visible during runtime, but it is only used to specify values. Yep. So look at these as constant definitions in C and C++.
gotcha.
Yep. All right. So the next member of a date is month. Okay. So I can just say 1, okay, but in order to represent that this is the one element right after this one, and that particular member has 1 byte, I'll use this representation, okay, because it is 1 byte off from the first member of the structure. And then the last one is DOM, and it is 1 byte off of the month member of a date structure, okay. And we have one more label, okay, we'll have a label called size, so that we can actually tell how many bytes a particular date structure should take. So that would be the last member plus the size of the last member. So that would tell me how many bytes a particular date structure is going to take up. So are we doing okay so far with these label definitions? So the label definitions do not generate a single byte of opcode. It completely disappears during runtime. Yes?
For the definition of date size, you said it was the last member plus the size of the last member.
Yes. So date DOM is the displacement from the beginning of a structure to the beginning of the last member. This one here is the size of the last member. So when you add these two, that becomes the size of the structure itself. Is that okay or not?
I hope I'll understand it.
Okay, maybe a picture would help. So let me use a picture. Okay. Okay, so if I use a picture, okay, page new. So when you look at the structure, and I'm going to use the same convention as I usually do, what is lower would be lower memory addresses. So if this is the beginning of the entire structure, okay, it kind of makes sense that the first member is at the lowest possible location, right? So the lowest member, or the first member of the entire structure in this case, is YS 1900. So this byte is YS 1900. Okay, the next location will be the second member of the whole thing. So in this case, it is month, and then the last one is DOM, right? So when you look at, where can I find YS 1900 if I know the beginning of the entire structure? It is at the displacement of 0 from the beginning of the entire structure. Where can I find month? It is at 0 plus 1, because the plus 1 has to do with the size of YS 1900 itself. Where can I find DOM? It is 1 byte past the beginning of month. Where do I find the end of the entire structure? It is where I can find DOM plus the size of DOM itself.
Okay, so I could think of it like the marker at the end of an array saying this is how large the array is.
It marks the size, of the whole thing. So, you don't want to treat it as an offset, because it would be the offset of the next thing, whatever it is. So are we good so far with this picture? Does everybody get this one? Yes? Okay, all right. So we switch back to the C code and continue to translate the code that we have. So I'm not going to implement isBefore first, because the first thing is to implement main. So just like usual, with a no op, because I'm assuming that I might want to run this on the command line, so a no op is necessary. LDID with 0 to emphasize that we are initializing the stack pointer to be as high as it possibly can be. So now we have a little bit of an interesting question. How do we declare or allocate space for local variables? But we have talked about that already. It's on the stack, right? So we'll do it on the stack just like before. But now the question is, but how many bytes on the stack? Okay, because before we have only been allocating for local variables that are byte wide. So now we have a whole structure. How do we deal with this? What do you think? It's based on date size. Okay, so what instructions should I use to allocate for the two local variables? Okay, so I'm asking you guys to kind of contribute ideas. I cannot see who. Okay, okay, go ahead.
I would think that potentially you would load date size into register A, add that to D as the pointer twice potentially. Subtract it. Or
Subtract.
subtract it
Yep.
maybe.
Mm-hmm.
Or subtract that D like 6 times. Yeah, or manually decrement D 6 times.
Okay, but that okay, decrementing these 6 times would get the job done, but as soon as I change the structure, that code is not going to work, right? So we want to make the code to be as uh, automated as possible. If I do decide to change the structure, I don't want to have to redo everything by hand. So this is the way I'm going to do it. Okay, so you guys got the idea, but there's a easier way to do it. So we have date size 2 times. It's not just addition and subtraction. We can multiply and divide too. Or if you choose, you can also do that works too. But I'm gonna go for 2x. Okay, 2 times. There we go. Okay, and then we decrease the stack pointer by that much, which means we're subtracting a from d. Okay, because we want to decrease the stack pointer by 6 basically to allocate for that space. But that means, I somehow need to, define some labels so I can find those local variables, quickly without having to maintain a mental picture. So that means, I can, now this is up to you, okay? The convention, there's no actual compiler convention that I know of which of the variable should have a lower address, okay? But if you think about what the compiler does, is it reads from left to right, top to bottom. So it kind of makes sense that text BD has a higher address because it's allocated first, and then Dave's BD is going to be the second variable, which has a lower address because we'll be allocating in the same order that we encounter those variables. So we'll just kind of follow that order in this case. Okay, so if that is the case, that means Dave's BD would have an offset of 0 from where the stack pointer points to after the allocation. Okay, and then we have tax, okay, BD being Dave's BD. Let's see, date underscore size plus, right? Does that make sense? Because we are looking at the offset from where the stack pointer is pointing to after the allocation. So these labels are applicable after line 11, because line 11 is the last line that we need to allocate the space. Yep.
So that's just separating the 6 bytes for yours and then.
Yep. So it's separating the 6 bytes so that the 3 bytes that are higher will be allocated to TAC, and then the 3 bytes that are lower will be allocated to Dave. And that's following this order. So TAC has a higher address because it is encountered first when we compile the code. Yep.
So if you initialize the label for date year since 1900 as 0, and then you also do the label for Dave's BD as 0, that works for that date for Dave's birthday. But what happens when you go to Tack's birthday and you want your, I mean, YS 1900 is 0, but that's now at memory location 3, right?
Say that one more time.
I'm just trying to think. So the first year since
Oh, on
1900.
which line? Tell me which line we are looking
Okay, so
at.
yeah, so for line one,
Uh huh.
where label is pointing to zero for year
Uh
Y
huh.
is 1900, you have the same for 12, line 12 for Dave's birthday pointing to his memory location
But they're
zero.
Well,
offset
yeah.
of different things. Yeah, go ahead.
So my question was basically, you can do that.
Yeah.
So when we decrement D enough, then you can just say, okay, now the offset is just starting from that point.
Yeah. Yep.
Okay.
Well, I mean, a label, remember, a label is a symbolic name of a numerical value. That's all it is. Okay? How you use the labels, what you want to use the labels to represent, is entirely up to you. So we can use labels to represent offset of a member from the beginning of a structure. That's how we define, quote unquote, a structure in assembly. But we can also use a label to define, how far is a local variable from where the stack pointer is pointing to. So that's what we're doing on line 12 and line 13. Because how you use a label is up to you. A label is no more than a symbolic name that has a numerical value that can be computed in this case, but it is nonetheless a value that is determined at assemble time.
Okay.
Okay?
Yeah.
Yeah, go ahead.
How would you use that? How would you use the label then?
We'll get to that when we actually have the initialization stuff. But I do want to kind of show you guys what the stack would look like. So this is basically, okay, this part here, which is really a template, this is struct, okay, or class in a object-oriented programming class, is a cookie cutter, okay? So a cookie cutter is useless unless you stamp cookies out of it. So in the analogy of cookie cutter, cookies, and cookie dough, okay, what is what in this class? The label definitions related to the displacement of each member from the beginning of the structure, that's your cookie cutter. It is a template. It tells you how to interpret different bytes at different offsets from a certain location. So that's your cookie cutter. Memory, okay, locations in RAM, that's your cookie dough. What about a cookie? Dave's birthday is a cookie. Tax's birthday is a cookie. It is cut out using a cookie cutter, but nonetheless, it is going to use cookie dough. Is that okay? Are we good so far? Because most of these analogies would actually carry over to object-oriented programming as well. It's just that we are dealing with much larger things instead of tiny little things that we're dealing with in this class.
I guess I'm just curious that YS 1900 is going to work for Dave's birthday, where his memory location zero.
Okay, so let me show you another picture. So this is the picture of a stack. Okay, so this is a picture of a stack, and we have this is the top of the stack, and this is the second portion of the stack. Okay, this is where you will find Dave's birthday, birth date, and then this is where you find tax birth date at runtime. Okay, this is location 100 in hexadecimal. So this byte here is FF, this byte here is FE, this is FD. And then you subtract 3 from FD, so that you get, so that's FA. This is byte FA. Is that okay? So there are 3 bytes to each structure. Let me choose a different color to kind of emphasize. The red line is indicating the boundary of a structure. So now we have 2 structures on the stack. So if I know where is the beginning of an entire structure, how do I find a member of that structure? That is what the date underscore stuff is about. Is if you tell me where tax BD is, okay, I can then tell you where to find YS 1900, where to find month, and also where to find DOM. Is that okay? So the 2 sets of labels serve different purposes. One is where do I find the local variables, knowing where the stack pointer is. Okay, that's tax birth date and Dave's birth date. The other set says if you tell me where the beginning of a structure is, I can help you find the members of a date structure. That's what the date underscore labels are about.
Yeah, I guess that's my confusion, and I'll probably see it when you actually implement the labels. But
Uh huh.
but are you at some point then changing the value of that initial
Oh yeah, I mean, we're gonna do all the C code in assembly. So we'll get to that. Okay? Are we good? Okay. So keep that picture in mind. Okay, I cannot really show more than a few things at the same time just because of the projector size. In the new building, I have already asked to have like multiple projectors, like 2 of those, so I can have one to stay on the source code, the other one stay on the picture, so that way we can actually see multiple things at the same time. But capturing that is going to be interesting as well because now we have 2 streams, and I'm pretty sure OBS can handle that too, so should not be a big deal. The question is, do we have the money to do it? And that's why there's a fundraiser, to collect money to help raise fund so that we can buy stuff that is inside the building. We got the money to have the building built, but the rooms will be empty. There will be no chair, no desk, no projector, no projection screen, no whiteboard, nothing. So we're trying to do a fundraiser for that. All right, so now we get to the first instruction, okay? After the first one, the rest are pretty boring, okay? So we're only interested in the first one. So with the first one, okay, actually, by the way, I used the wrong syntax because these are all supposed to be dots. Because Tech Speedy and Dave Speedy are not pointers, they are actual structures. So in C and C++, you use a dot when you have pointers, and then when you have actual structures, and when you have pointers, you use the dash greater than.
Okay, so that's the difference between the dot notation and the pointer notation.
Yes, which is really annoying. Yeah.
So if in your struct, if you had made that like star year 1900 star month star dawn, then they would be with the pointer.
Yes, syntactically that would be correct. Okay, so don't copy this. Okay, I'm just gonna mention what would happen. So let's just change one of them. Okay, so if I change text BD to be a pointer to a struct date, then to correctly use the type of that local variable, I would have to change all of these to a dash right. I mean a right arrow basically, but it would not work correctly because as a pointer, text BD is uninitialized. So that means, I'll be going to some place that a dangling pointer is pointing to. So I'll just be randomly modifying some 3 locations. So that would not be good. But in terms of how you use a variable of a type of pointer versus how you use a variable that is of a type that is a structure itself, that's the differentiation. Is that okay? Yep, go ahead.
In the actual structure itself.
Hmm?
What about in the actual structure?
The actual structure? You mean at the beginning of the code?
Yeah.
Okay, so let me fix this first before I forget. So we'll change this back to an actual structure. So now, tag as a local text BD as a local variable is a full structure. It will take up 3 bytes. So are you referring to this part? This is the cookie cutter, which means we don't need to, get to any one of these parts because you're only talking about a cookie cutter. So we only want to refer to a part when you have a piece of cookie cut out by this cookie cutter. Is that okay?
Like if one of those was a pointer?
Yeah.
If one of those is a pointer,
Would you have one of those be a pointer
it can be.
and then so how does that change?
It wouldn't change how we access the member itself, but it would change how the member can be used. So we can get to that in a different program. Okay, so getting back to the code that we are writing here. All right, so okay, let me move this back to where we are supposed to go. So we are implementing, or we're trying to implement line 45 at this point. Okay, so we'll go ahead and implement line 45. The right-hand side is really easy, so I'm gonna defer that to later. Okay, so we'll compute the L value on the left-hand side first. Where do I find YS1900 as a member of the structure that we know as text BD, which is a local variable on the stack? That is what we want to do. Okay, so what you knew from before would actually work really well. Okay, so we'll go like, okay, LDIA text BD. Okay, remember this is how we access local variables and also parameters. Okay, and then we have to add AD, right? So at this point, okay, so don't copy this because I'm going to make some modifications. But if you want to copy, that's fine. You just have to leave some room, so that we have room to change it. So at this point, okay, given this is the code, then we have this. Are we good? Because that's the whole purpose of defining the labels the way that we did, is to say, okay, each one is a displacement or an offset from where the stack pointer points to the variable that I want to access. So I just load the offset into A, and then I add the stack pointer to A. So now A has the address to the local variable. But the local variable is a structure, okay? And according to this code here, I don't need the entire structure. I just need one member of the entire structure. So now the question is, how do I get to just that member, or the address of just that member? There are two ways to do it, okay? So the long way to do it is to kind of do it like this, okay? It is a little cumbersome, but it works. So we can now add date underscore YS 1900. We will load it into register B because then we can add B to A. So now A is the address of tax BD dot YS 1900. Does that work? Okay, because given that at the end of line 16, register A has the address of the structure itself, all we have to do is to add the offset to a member to the entire structure, do the address of the structure, then I get to the address of a member. Are we good so far? But this code is redundant, okay? A lot of this code is kind of redundant, because I could have, if you look at tax BD and also date underscore YS 1900, both of those are constants. And instead of using two add instructions to add constants to a particular register, I could have just added the constant on line 15. So this code works, okay? It is a little bit clear of what each label is, and step by step how we get to the address of YS 1900 as a member, of tax BD as a structure. But the much more optimized version, I'm going to do it separately so that people can have a chance to compare and contrast the two approaches, okay? So I could have just do this as well and get rid of these two. And then change the comment, obviously, because now we have the address of member 1900 YS 1900 of the structure tax BD. So this is the faster way to do it. It is much more direct, but the other way is kind of step by step, and it explains how we use each label. Okay, I cannot tell who's first. Okay, go ahead. There's no inline modification though. I'm not changing the label definition. I'm referring to the value of a label. Are you referring to line 20? Yeah, line 20 is fine because tax BD is really just a number, and so is date underscore YS 1900, and that works. Because I'm not changing the definition of a label, I'm only referring to the value that a label is defined as. Yep, go ahead.
So this is how you specify which spot on the stack is what. So since you're doing tax BD, which is the lowest part of the stack, and then adding it to the date, which is right on the top, so that's how you specify. Okay, that makes sense.
That's how we get to the address of a member that is of a structure that is a local variable.
Okay.
Yep, go ahead.
I'm not sure what I want to ask.
That's okay. Take your time.
Well, okay, so are there instances where we can't do arithmetic? Because is it correct to say that one of the parameters, that the parameters to like LDI can be more complex?
Because of the immediate. So if it's an immediate, that means you can have an expression, a general expression, but what you can use in the expression are limited to constants, label definitions, or label values of labels and operators. So you cannot have register A as a part of the immediate part of LDI because the value of register A is a runtime construct, and that cannot be determined at compile time. So whatever you specify as the second operand of LDI has to be an expression that can have its value resolved at assemble time, can be done statically, cannot be something that relies on the runtime value of registers. Okay? Are we good so far? Okay? So the rest is really not very exciting because now we LDIB with the right hand side value, which is just 66, and then we do a store, and that's done. And the other five lines are really the same thing, so they're kind of boring, but we'll do it anyway. Okay, so we'll go ahead and copy and paste, and this time we deal with month, and the month is supposed to be October. Okay, so some people might observe and say that, hey, date YS 1900 is just 0, so why even specify that? It's because now we have a template. Okay, regardless of which member we are referring to, we just apply the template. That makes it easy. No special case to memorize and no special case to look for. Okay, so now we can copy and paste this again to deal with DOM. And that's supposed to be just 1. And now we got TAC birthday initialized. So to get Dave's birthday initialized, well, just copy and paste, and then change tax to Dave's. Okay. And then change the constants, how we initialize those. So 90 July 23rd. There we go. So a bunch of code, yes, it is kind of long, but the approach is the same. Are we doing okay so far with this? Okay, so main is done, all for the most part, okay, except for the function call. So the way we do the function call is not really that much different compared to swap, because we are not passing something by value, we're passing something by reference, so by pointer to be exact. So the way we do it is, okay, LDIA with Dave's BD, because that's our second argument, it is pushed first. So this time we don't add a displacement because we are referring to the address of the structure, not the address of a member of the structure. So we just do the usual stuff, okay, add AD, that becomes the address of the structure. Now we just have to push it on the stack, decrement D, and then we do stda. So this is what's going to push Dave's birthday on the stack. So now we have to be careful because now we got one extra thing on the stack, which is the argument to call is before. So the way we calculate the address of tax BD is going to be, well, I wouldn't say too tricky, but we just have to keep in mind that we have to account for that one extra byte that is also on the stack. So we have to remember the 1 plus because the second argument is on stack already at this point. Are we good so far? Does everybody understand why we have the 1 plus? Okay. So see the decrement D right here on line 52? That changes everything because tax BD is a displacement to the first byte of the local variable structure, right? But that's a displacement from where the stack pointer points to right after we do the allocation for the local variables. But the stack pointer just changed. It just moved down by 1. Is that okay?
Can you show where you initialized it with that up above where you initialized the object?
How we define tax BD?
Yeah.
Okay, we can show that, but that's really kind of not important in the discussion, though. Nope. Because this is constant. This cannot change once the label is defined. It cannot change. It doesn't care about runtime behavior at all, right? But this is a displacement of tax BD from where the stack pointer points to. But that's referring to the stack pointer after line 11 executes. Is that okay? But the stack pointer can change during runtime. And when we get back to where we left off, on line 52, the stack pointer got changed. It decreased by 1. So that means if I want to get back to the same location, I now have to add 1 more to whatever the label is to account for that 1 byte that is now pushed on the stack. It's kind of like saying what is the altitude? Not altitude. Is it altitude? Altitude. Okay. What is the altitude of a house? Okay. I am 15 feet. So you can have an absolute measurement. Okay. But you can also have a relative measurement. So let's say the relative measurement is against water level. Okay. So you can say, oh, my house is pretty safe. It's 10 feet from water level. But if the water level drops, okay, then the way you calculate where your house is need to account for the drop of the water line. If the water goes up, then you have to account for that too. So this is what we are doing, is to account for, oh, there's more things on the stack now. The stack pointer is now lower, so we have to account for that 1 extra byte that is now on the stack. Yep.
I was thinking of it kind of like you set a stage, you have all your props out, and then the actors come out, they're doing stuff. Someone lowers the curtain a little bit, and well, okay, now it's not set to the correct place, and so you have to account for that. Because if you
Yep.
were to lower it or whatever the wrong amount, then everything else would fall.
It's because it's all relative to the stack pointer. So when the stack pointer changes, then you have to adjust for that change.
Yeah, and changes happen during runtime. Like
Exactly.
accurate way.
Yep. That is exactly why. But the rest would be the same. Okay, so we just add a D, decrement D again, because this time we have to push it also on the stack. So this part is going to push the address of tax BD on the stack. And then we push the return address. Okay, so that part it should be fairly kind of boilerplate at this point. So .5 plus. And remember that there's no space between the comma and the dot, but there is a space between the dot and the 5. Otherwise, it won't work. And then we stda, and then we do a jmpi to is before. And then after that, we increment the stack pointer twice to deallocate the arguments. So right now we have just the local variables still on the stack. And at the end of a subroutine, I know main is not exactly a subroutine, but we'll treat it as such. So we have to deallocate the 2 local variables as well. So that's why we have the LDIA with, well, let's use B. So this way, I preserve the content of A, so we can actually see whether it's returned true or false. So we'll LDIB with date underscore size 2 times, and then this time we add, okay, because we're deallocating, we'll add this to the stack pointer. So at this point, the stack pointer should be balanced, which means if it started off with 0, after line 69, it should be 0 again. Do we have any questions? So this is all seen from the perspective of the caller. Yep, go ahead.
What's happening on line 61 again?
Line 61,
Yeah, 61. LDIA or
dot 5 plus,
plus, yeah.
that's for pushing the return address.
Okay.
So these 4 lines from line 60 to line 63 is kind of boilerplate for calling a subroutine. Yep.
If you ever lose track of the position for the stack pointer, how would you find that? Like, how would you? Do you just have to kind of keep track of it in?
Yep, you have to keep track of it. So whenever you decrement D, you know the stack pointer is lower by 1 byte. Yep.
You could declare like is before that, and then just use that LDI. Like you could declare like the return address before decrementing D, right? And then set like the where it is on the stack, and then loading it into A, right?
You could do that because, okay, so you're referring to these 2 instructions. You can exchange the order of these 2 instructions, but if you do, the .5 plus will become .6 plus because now you also have to count the byte that the decrement D has.
No, I mean, like if you declared is before as a label, and then
You cannot declare A as a label. A is a
no,
register.
before.
Huh?
If you declared is before as a label, like they use the is before label and then specified where it is on the stack, couldn't use that, load that into A?
No, because that's the destination. That's where you're going in the subroutine. This is specifying where it's supposed to go back to when is before is done.
Okay.
So this is the return address. This is where we're going. So there are two different things. This is where we get to the destination, and this is your ticket back to where you were.
Yeah, so instead of having a return address label, we do LDIA dot 5 plus to come back after the jump, because jump is before says we're going into the subroutine is before. That's what that means.
All right.
And instead of having a return address, we just do that line 69.
Are we doing okay?
Yeah, no, I'm good. I was just curious
Okay.
if you could do it the other way.
Okay. So now we're going to talk about is before. Okay, I'm just looking at the clock. We got plenty of time. We can finish this. So is before is really not that complicated. If you look at what is on the stack, when is before is at the entry point, you get the usual stuff. You get all the arguments, right? All the parameters. Excuse me. We have two parameters, PD2 and PD1. So we got PD2, PD1, the return address, and the return address is where the stack pointer points to because it's the last thing that we push on the stack. So this is what the stack looks like at the entry point of is before. Are we doing okay so far? PD1 is a 1 byte thing. It is just the address of a structure. It is not the structure itself. PD2 is really also a pointer. It is not the structure itself. So in an 8-bit architecture, each address is only 8-bit wide. So that's why we have this picture here. Is that okay? All right. So the next thing we do is to define some labels so I can locate my parameters more easily. So we'll define return address, which is at the lowest point of the call frame, for this invocation, is 0. PD1 is 1 byte after that, and then PD2 is 1 byte after PD1. Okay, so that's how we define those labels. So once we have the labels all defined, now we have to get to the member of the structure pointed to by a parameter. It's a long way to say it, but it's not really that hard. So let's go ahead and try to load this into register A and try to load this into register B so that we can do the compare. Okay? So let's go ahead and figure out how to do this. Okay? So if we need to get to the member called YS1900 of the structure that is pointed to by PD1, don't you think we need to get to PD1 first? Yeah. Okay, so let's do that. So how we get to PD1 is really the same thing that we do to access any argument, okay, that we have done in this class. LDIA, okay, with PD1, which is a displacement from where the stack pointer points to the parameter that is on the stack. So now we have to add AD. So now register A is the address of PD1. Good. PD1, we got PD1 loaded into the address of PD1 loaded into register A, but I'm not interested in the address of PD1. I want to know what it is, okay? So LDAA would now say A is, okay, in long term, it is the dereference of the address of PD1. Oh, you mean that's really just PD1. But what is PD1? PD1 is a pointer. It is the address. So A now has the address of a structure. Is that okay? I'm not interested in the entire structure, okay? Because in C code on line 10, I'm only interested in the member called YS1900. So yeah, it's going to fix itself. I think it's a temperature thing. There we go. So we are only interested in a member of the structure, and I know the address of the structure. But before I can get to the value of the member, I need to know the address of the member, right? So how do we get to the address of the member called YS1900? Use label offset. Okay, so now we need to use another register, okay, because I cannot use register A again. So this is where I'll use register C, which is date underscore YS 1900. And yes, I know it is 0, okay, but that's a special case. I don't want my code to only work for special cases, so that's why I'm gonna do it this way. So at this point, A is the address of PD1 points to YS 1900. In other words, now register A has the address of the member that I'm interested in, not the value yet. Are we good so far? All right. So after this, I have to do another LD, AA. So the A finally is the dereference of the address of member 1900 of the structure that is pointed to by PD1. And I think I said it right. Do you want me to do it again? Yes, I can. So we are dereferencing the address of member YS 1900 of the structure that is pointed to by PD1. Which otherwise is also known as PD1 points to YS 1900. So we get the value now. Okay, A finally has the value of the member that we want to access. So this particular sequence of instruction is really important. Okay, I'm still recording, by the way. Okay, so you might want to kind of review all this stuff here, because every single line is important. Okay. Huh? In this case, I have to use the right arrow because PD1 is a pointer. Now the pointer thing, okay, in terms of C syntax, just so that you know, instead of using the pointer thing, the alternative is to say, let's dereference it first, okay? Because after you dereference, you're referring to the entire structure. Then you can say, I just want to access this member of that structure. So syntactically speaking, they look different, but semantically, they mean exactly the same thing. I mean, you can actually run the code and verify that they actually do exactly the same thing. Only C and C++ has this particular construct. Java, JavaScript, and almost every single scripting language out there has the concept of a reference, which is sort of an address, but they still use a single dot to access a member of an object. So C and C++ are the only languages that makes use of the pointer, symbol to basically say the member that is of a structure pointed to by a pointer. Okay, so how do we get to the other one, the other thing that we are supposed to be comparing against? Let's change all the register A to register B. And then we change PD1 to PD2. So that's how we do the same thing. You can see how, after this point, it's just going to be a little bit boring. Oops. And this is PD2, 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 and register B, and register B.
One more to the left.
Huh?
On 92.
92. Oh, okay. There we go. So now that we have register A being the left-hand side of the comparison and register B being the right-hand side of the comparison, we can now do the actual CMP instruction. Okay. So now the question is, which way do you want it? Do you want a CMP BA or do you want a CMP AB? See, it's filled with choices, right? Okay. And no matter which one you choose, we can still make it work, okay? But we kind of want to make this work the usual way, which means we're looking for an excuse to go to else, okay? That's the usual way of doing things. So the excuse to go to else is to say, oh, we're looking for greater than or equal to, okay, to kind of go the other way. So if you're looking for greater than or equal to, if you're looking for PD2, YS1900 is greater than or equal to this one, it is more convenient to specify BA. Let me think about it. If this one is greater than or equal to that one, that means the other one is less than or equal to the first one. So this makes more sense. So now you can use a JCI because they are unsigned. The members are unsigned to go to else1. Okay, we'll define else1 to be here. But wait, there's one more reason to go there. JZI to else1. Is that okay? Else1 is referring to the else of the outermost conditional statement. And from here, we have an unconditional branch to end if 1, which is all the way to the end of this entire thing. And over here, we can now finally specify, okay, what value am I supposed to return on line 12? Some non-zero value. Are we good so far? Yes? Maybe? Okay, so what goes in here? That would be the entire else branch of the outermost conditional statement, starting on line 16. You look at line 16 and go like, oh no, we have to recompute everything. Nope, they're still in register A and B. And also, nope, we don't need to compare again, because the flags are still effective at this point. The flags that are set by the compare instruction of line 94, they're still here. By the time we get to line 100, we still have those flags the same way they are set after line because of line 94. So we don't need to compare again. We don't need to load anything to register A or B. We don't need to even compare again. All we need to do now is to say, well, it's either greater than or it's equal to, right? Because we have already ruled out less than. So we can now say, if it is equal to JCI, then we go to the else of the else. So it becomes else1, else1. Okay, else1, else1 is going to be here. What if we're not branching to else1, else1? Then we're going to the then branch of the else branch. It is the else of the outermost, but it is the then of the second level of conditional statement. So what do we do on line 19? Oh, we need to return 0. Okay, fine. Specify the return value, and then we are supposed to jump to the end of the second conditional statement, so it is technically it is end if 1 of else 1, because it is the end of the conditional statement that is part of the else branch of the outermost conditional statement.
I understand the words you said.
Okay, so we have a lot of conditional statements. So how you choose the label names is now kind of important, because if you just sequentially use L0, L1, L2, you're going to have a hard time remembering which one is which one. Line 10 is the beginning of the outermost conditional statement. So labels related to that particular control structure is going to be else 1, and if 1, and if I need to, if 1. Yes?
Is there any restrictions on label naming?
Nope, there's no practical restriction of how long that name can be.
Like do else 1.1 and then
I'm not sure about point. I don't think you can use point, but you can use underscore.
Okay.
So if you can use a name as a C identifier, you can use it as a label name. That's kind of the rule.
Okay.
Yep. Go ahead. Oh, okay. All right. So now we're in else 1, which is the else branch of the else branch. So we got to the else branch of the outermost conditional statement, and now we are in the else branch of the first level or the second level conditional statement. So let me switch to the C code so that we know what we're talking about. We're talking about line 22. So line 104 is corresponding to line 22 of the C code. Okay? So at this point, yeah, we kind of have to do things all over again, which is kind of cumbersome. So if you don't want to do things all over again, you can store the address of the structures into specific registers, so you can actually just retrieve those, as local variables. Yep.
Oh no, that answered it.
Yeah. So you could do that. I'm not sure how many instructions you're actually going to save, just because of that. Okay, you might save a few bytes, but not really a whole lot, because the parameters are already the address of the structures, right? And if your local variable is storing the same thing, you're not going to save a whole lot. So what we'll do is copy, paste, and modify again, like on a massive scale. I probably could copy and paste even the rest, but I'm not going to do that. So I just copy and paste how we load values into register B and register A. So the first one, but the modify. Excuse me, this is going to be really bad when you listen to the recording. Okay, but the only change we're doing here is the month. Okay, which member are we referring to? Because hey, we can keep everything else being the same, and we'll change the comments. Could have used search and replace. If I were using VI, I would have done that. But this is not my favorite editor. So we'll do it the kind of long way. There we go. Okay. This is just to make sure the comment, does match the code itself. So now, once again, let's see, I missed one thing, sorry. I apologize, because, I have to jump to the end of the conditional statement that is in the else branch of the outermost conditional statement. And that label is supposed to be defined here. So we have else one and if one defined right here, which is really the same place as and if one. Okay. All right. So now we have A and B, initialized to the month member of PD, what the structures pointed to by PD1 and PD2 respectively. And so we can do the compare. Okay, same deal, compare B to A. If it is less than, let's go to the else case. So now, how do we label this else branch? It is, we are in the else branch of the outermost conditional statement, and in the else branch of the conditional statement that is nested in the else branch of the outermost conditional statement. And this is the else branch of that conditional statement. So we are talking about else one, else one, else one. Now the one is sort of important, because what if you have multiple conditional statements that are in sequence? Then you have else one, else two, else three, and so on. So this is really, it's kind of the same kind of notation that lawyers use in law documents, right? Because in law documents, you have to be able to refer to a particular clause of some paragraph in a very precise way, right? We are doing the same thing, okay? Yeah, just so that the label name reflects the structure of the code. JZI, do the same place, okay? Because those are the conditions to go to the else branch. So now, what if we do not go to the else branch? That would correspond to line, let's see, we're dealing with month. So we're dealing with line 24 here. So line 24 says, let's return a 1. Okay, so LDIA with 1. And then we have to go to the end of the conditional statement that is 3 levels down. Okay, so we have to do a JMPI to else 1, and if 1, which also turns out to be here. Else 1, and if 1. Okay. Then we have to also define the else branch. Okay, where is the else branch? Else 1, else 1 is here. So that would correspond to the C code starting on line 29. So on line 29, we just have to say, hey, if it is equal to, because we know at this point it's either equal to or greater than. If it's equal to, we go to yet another else. Okay. So we say JZI to else one, else one, else one, else one. Because we have 4 levels of conditional statements. We can go back to the C code and check to make sure that we do have 4 levels of conditional statements. If we do not branch, then we're supposed to just return a 0. So load A with 0, and then JMPI to the end of just that conditional statement, which is else 1, else 1, else 1, and if 1. And that's going to be defined here as else 1, else 1, else 1, and if 1. And now we have to define else 1, else 1, else 1, else 1. Ah. All right. So that is corresponding to line 34. Sorry, go ahead.
So like watch video again, put the date and time.
That's part of why we do the recording. So now we are on line 128 of the assembly code. That is corresponding to line 34 of the C code.
I thought you said the assembly code was supposed to be easier.
It depends on from whose perspective, right?
Well, I mean, there's less parentheses and brackets.
There's more else one though. A lot more else's.
Yep, that is true. Okay, something is not right. They're not lined up. Okay, there. Okay, there we go. Okay, I got it. Okay, so now we need to reload DOM. Okay, this is not too hard. Okay, this we can do this. Okay, we're almost done there. Okay, so we are now at the else one, else one, else one, else one, and we are gonna change all the months to DOM. So I'm gonna give it a try and see if I can search and replace. And we want to replace all in selection. Very good. And we're looking for month, and replace all of those with DOM. Search direction is down. I don't think that really matters. And whoo, done. Okay, so now we have one last comparison, okay? So we have one last comparison, and we are returning a non-zero if DOM is if it's less than, and for all other cases we want to return a 0. So we'll just kind of do it a compare AB, okay? But we can only use JCI, okay? So JCI to return 1. And then over here, we LDI A with 0 and return a 0 instead. So JMPI to, okay, all done. Or if you guys prefer, else 1, else 1, else 1, else, and if 1. There we go, and if 1. Okay, so now we can finally, we're all done. And here's the label called return 1. LDIA with 1, and we are all done with the subroutine. Oh, I got the extra colon where it's not supposed to be. There we go. So this is it.
It's only like 5 times the amount of lines of code.
Well, that's why you need to appreciate the compiler.
Appreciate Control C, Control V.
But do we have any questions? But the main point of this entire lecture is how do we get to a member of a structure that is pointed to by a pointer that is a parameter. Okay. Now, I know, it sounds really bad, but if you follow one step at a time, it's not too bad. I know we are running out of time, so I cannot do it in class. But when you are studying, okay, when you're reviewing all of this stuff here, it really helps to draw a picture. Okay, draw a picture. This thing is pointing here, and then we add this displacement, it becomes that. Okay, because once you have a picture, it really helps to visualize, what each thing is and how a register changes over time. Okay, so I don't quite have time today to draw the picture and also draw the transition of how one register is changing, what it is, depending on which step we are talking about. So we could do that next time on next Monday. Next week is our last week, so that means we will have a final exam review on one of the 2 days next week. But I do want to finish the discussion of structures because it really helps you to understand what structures are. And then on top of that, I also really want to have time to talk about the program. Did I talk about the hacking program? Of the link is here already, but you guys probably do not know what it's for. It's called hack1.strip. Do you guys remember that? Yeah, hack1.strip. Um, it's a program that I wrote, okay, and I threw away the source code. I threw away the symbol table within the executable, so there's no help for me. There's no help here except for my really poor memory to help me crack the program. All I can remember is the approach. I cannot remember exactly where to find something. Okay, so hopefully next week on one of those 2 days, I'll have a chance to demonstrate how to hack a program and utilize what we have learned in this class. Okay, now it will bring out, you will need to know a little bit of the mnemonics for the x86 architecture, so I will explain that a little bit, okay? And the content of hacking this program will not be in the final exam, so don't worry about, oh, so now we have to finally learn another architecture. Nope, you don't have to. But I do want to demonstrate the approach because some of you may be interested. It's like, oh, so if I know how the stack is used, I can potentially do these things and, yeah, so it's going to be fun. All right, so you do have the new homework assignment. It's due in a week, which is next Wednesday. I can push that out to the final exam date, okay, which may or may not help in any way. So we'll go to the lab. You do have a new lab today, which is on structures. Nothing quite this bad, okay? Well, actually, I take it back. It is a little bit different, okay? I wouldn't say it's as bad, it's different, okay? So we'll get to the lab and get started with that lab.